Hello, AP Chem. It is Thanksgiving week, and we are here to talk about vapor pressure of solutions. So let's get right into it. Thanks for joining me. This is to help with the last assignment, assignment 10, and the last little bit of content of unit 3 that we're going to be doing this semester. So we're going to start with a little thought process here. We have 3 different solutions. We have pure water, which, as we know, will have a little bit of have a small vapor pressure above the solution. And we have water that has a non-volatile solute, such as like sodium chloride, some sort of salt, dissociating salt. And then we have a third possibility where we have a mixture of liquids that dissolve in each other, which we call miscible. And so we're going to try and compare their vapor pressures from both of their original vapor pressures and what is their combined vapor pressure. So we'll start pretty easy. What we've done so far is basically say if we have water and we have pure water, and we've done some gas collection over water, but we basically look up some sort of textbook value, and based on some given temperature, we know the vapor pressure of water above a solution. And that's all that represents in some sort of closed system, how many gas particles are above the liquid. And this has formed some equilibrium. So as water evaporates, some vapor is condensing. And so this rate of evaporation condensation is equal to each other. So there's always some vapor above the liquid based off the temperature. So this is pretty straightforward. Usually this pure pressure is a given value, and we know it's a pure pressure by this little degree sign above the P. So it says it's pure vapor pressure of water. So we need to know this value, and basically what we're going to do is see how this value changes as a result of adding ions. So when we have some sort of ionic compound, so there's going to be some cations, there's going to be some anions. There's a couple of things to consider. First of all, when the cations go in, they separate. And they get surrounded by water, and these ions are filling the space. And there's some sort of saturation point where at some point I can't dissolve any more ions. We're just going to assume everything dissolves, and we don't have any undissolved solid, even though that wouldn't really affect the vapor pressure at that point. But what we need to know is how many ions are dissolved in solution. And for the vapor pressure equation that we're going to see, it doesn't matter what the solute is, just how many ions are actually released in solution. And what we'll see is that vapor pressure is always going to decrease as the number of ions, as the concentration of ions increases. More ions in solution, that vapor pressure goes down. The particles are fighting against the intermolecular forces of the ion dipole forces, typically if you have an ionic compound. And it makes it harder for water molecules to escape. If you have some non-dissociating solute, like sugar or carbon dioxide, it still affects the vapor pressure, but not as much. And then we're going to get into 2 different liquids mixed together, this third example on the far right side, where maybe one of them is water. So we have the vapor pressure of water. We know what the water's vapor pressure is. So I'm going to label this pure pressure of water. And then so that's vaporizing. And then independent of that, we also have some vapor pressure of our other liquid. We're going to say this is some sort of liquid A. And that's also vaporizing. But based on any sort of intermolecular attractions between them, it might resist some vaporization. And we have the way of analyzing so that combined vapor pressure above the solution. We have the vapor pressure of gas A and the vapor pressure of water. Those are both adding to some total vapor pressure. There is a chance of this vapor pressure being higher than water or lower than water normally. It's based on whatever this other substance is. And it doesn't even have to be water. It could just be two liquids that are soluble with one another. So they're both polar or they're both nonpolar. So the most common example that we're going to deal with is this one in the middle, where we have some sort of dissociating salt or some sort of soluble salt that is non-volatile. And non-volatile means it's not going to have this, whatever solute you put in there doesn't have a vapor pressure. The vapor pressure is still just the solvent. And so we can base that calculation on that. So we're going to run through a couple scenarios. I'm going to go through the PowerPoint, and we'll go through some textbook questions, and we'll try and get you all set up to finish this over the break. So the first step is going to be to identifying how many ions are released in solution when we are dissolving a solute. So here's some sort of solute, and dissociation or dissolution means that we have a strong electrolyte, meaning that any sort of strong electrolyte is going to separate into ions in solution. We practice some of these equations. We always need to be able to just identify what is the right side going to look like, and I'll do a few examples of these. And so let's assume that we have 1 mole of the solid, and we're dissolving in water. HCl has 1 cation and 1 anion, and we can separate it into H plus and Cl minus, and these ions are always aqueous. And so 1 mole of the HCl will separate into a total of 2 moles of ions. We have a coefficient of 1 and a coefficient of 1, and 1 plus 1 is 2. So we have 2 moles of ions. So essentially what we do is whatever based on that given value of the salt ionizing or dissociating, it's going to have a times 2 effect on the how many moles for our calculations. Sodium hydroxide has 2 ions. First one is sodium, and so we get 1 part sodium and 1 part hydroxide. So whatever moles are dissolving, it's going to double how many particles are going to be in solution after it all dissolves. So it has a times 2 effect on the original mole value. Calcium chloride is commonly used in ice, in melting ice on roads, because 1 mole of the calcium chloride solid will separate into 1 part calcium and 2 parts chloride. So we get a total of 3 moles of ions for every 1 mole that we input. So once this dissolves, it has a times 3 effect on the total ions. And so the larger this effect, the larger this ionization effect, the more significant that's going to reduce the vapor pressure above water. Remember, we have our solvent, here's our water, and we just have our pure water. And anytime we add, if we add a times 3 effect in here, that's going to lower the mole fraction of water. And instead, and as a result, it's going to lower the overall vapor pressure. I mentioned freezing point and freezing of water and things like that as well. That also has a similar effect on the freezing point depression, boiling point elevation, colligative properties that are in the PowerPoint as well. But there's basically more moles of ions in solution has a greater effect on vapor pressure, has a greater effect on the boiling point changes and the freezing point changes. So it's all very predictable. Let's look at number 4. Before I do it, what is that multiplier? What is that? How many ions are being released in solution? Well, the sodium has a subscript of 3, so there's 3 parts sodium. But when you have a polyatomic ion like phosphate, so you have PO4, that whole thing has to stay together, and there's only 1 of those. So we have 1 part phosphate. Don't separate the oxygen from the phosphate. Phosphate is one of those ions that we memorized. So we still get a times 4 effect, which is pretty significant. But keep the phosphates together, the PO4s together. Let's look at number 5. How many total ions? Well, there's 1 barium and 2 acetates. So this has a times 3 effect on the total moles after it ionizes and separates and dissociates. Number 6 looks like a typo. Let's just ignore that one. Silver nitrate should be times 2. And chromium chlorate is a times 4 effect. 1 part chromium and 3 parts chlorates. Okay, so that's going to help us speed things up when we're looking at the mole fraction, which is part of the equation in the stuff I'm going to show you next. Let's get rid of some of these annotations. Okay. So here's Raoult's law. So here's one of the situations where we can just think of this conceptually. We have a pure source of water on the left and some sort of solution on the right. Whatever the solute is, there is solute in water. And so at all times for non-volatile solutes, which is emphasized right here, the vapor pressure of pure water is always going to be greater than the vapor pressure of some solution. What's vaporizing is still just water. The solute's there, it's reducing the vapor pressure, but we're still just talking about above the solution, it's only water vapor. We just get more of it from the pure source. So as time passes, the rate of evaporation on the pure water source is always going to be less than the solution. There's always going to be some particles in the beaker, but it's going to be essentially as approaches zero, as the rate of evaporation is always greater for pure water than the rate of evaporation for some sort of solution. Let's move on. So here's the equation for Raoult's law, and this is given on the AP test. So you can see on the right side of the equation, we have the pure pressure of the solvent, which is going to be mostly water in this case, but it's always based off the solvent. And this is the pure vapor pressure, and this is going to be given. So a big hint to use these equations is when they give you a pure vapor pressure of water. You have some sort of solution, and so the big math part of this, the challenge is just figuring out what is this mole fraction of the solvent. Now notice both of these are based off the solvent, which is typically water. Doesn't matter what the solute is, it just shows up in the mole fraction equation as it affects the mole fraction of the water in this case. So we're going to look at a couple examples. What we observe is the pressure of the solution, and this is that thing on the left side right here. This is what we actually observe. When we measure the pressure above the solution, this is the observed pressure. That's very important to distinguish. So we can do our calculations. We can have a pure pressure, we have the mole fraction, and we can calculate the expected pressure. So when we can calculate the expected pressure or the calculated value. And generally in the lab, what we'll do, or even in questions, we'll try and compare what do we calculate? What should we expect the vapor pressure to be? And then when we go ahead and measure it, what is the observed vapor pressure? These generally, in an ideal situation, these should be equal to each other, but in most situations they don't. And the reason for that are going to be any sort of interactions between any sort of additional interactions between the solvent and the solute, whether it's a stronger intermolecular attraction or a weaker one, could slightly change these vapor pressures. But just remember, in a lab setting, there's always some sort of percent error. So don't always expect these to be exactly the same. It's just we can always calculate what to expect prior to doing the experiment and look at what we observe. This idea is a little bit more significant with the last example where we have two liquids and they're miscible, and the vapor pressures may be slightly off from what we would expect. Here we go. So the presence of a non-volatile solute, remember that's a solute that does not have a vapor pressure. These are solids usually that dissolve in water. So you throw some of that in water and the vapor pressure of the water will go down. It's not the solute itself that's evaporating, it's just the solvent, that's water, that's evaporating. And here it is. The identity of the solute doesn't matter. Just the number of total dissolved ions is going to affect this mole fraction. So for example, if we put in 1 mole of sodium sulfide, you should have 3 moles of ions that you're using in your mole fraction calculation. So in this example that we brought up earlier with the 2 beakers, as time passes, pure water evaporates and enters the non-volatile solute containing the solution, making it more dilute. The vapor pressure of a pure solvent will always be greater than the solution solvent, even though it's getting more and more dilute. So let's do a couple example questions before we move on to liquids. Okay, so we're about here in the handwritten notes, and so I'm going to block off this lower section so we can just focus on this first practice question. It says, calculate the vapor pressure of the solution given some 30 grams of sodium hydroxide and 150 mils of water. So we're going to have to use a variety of tools to solve this one. And first off, I see the 30 grams and I see the compound there. So this is the solute, and 150 mils of water, which I know the density of water is going to be 150 grams for every 150 mils. And then it gives us this vapor pressure of pure water. You're gonna have to excuse me, I'm using my mouse for the writing. It's just a little slower. I don't have my Bluetooth thingy. So 30 grams of sodium hydroxide, when we convert that to moles, is 0.75 moles. You're going to divide by the molar mass of sodium hydroxide. Now, this is the moles of the compound. This is sodium hydroxide. So we're going to have to implement what's called the Van Hoff factor, which is the idea there's sodium and hydroxide in here. So you have to multiply this by 2 for how many ions this breaks up into in solution. So when you get 0.75 moles of the compound, that's actually 1.5 moles of ions. And that's going to be what we're going to use in the total moles calculation for the mole fraction, because we need the mole fraction of the solvent. So moles of ions, and then I went ahead and calculated the moles of water. So when you divide 150 grams of water, because the density of water is 1 to 1, 1 gram equals 1 milliliter. Every 1 milliliter of water equals 1 gram. That is something you should just know about water, just like you know the boiling point and freezing point of water in Celsius. So 150 grams of water is going to be 8.32-ish moles of water. You can see the moles of water is generally going to be much higher than the moles of ions, just because the water is so much more water than there is solute. And so the big thing for this one is we need to calculate the mole fraction of water and then multiply it by the pure pressure of water, and that vapor pressure of the solution, or the vapor pressure of water in solution, should go down. So here's the mole fraction of the solvent, which is water. So on the top, we're going to put water, which is the 8.32. And then on the bottom, we're going to put total ions, which is going to be 8.32 again, but plus our 1.5 moles of ions from the solute. So you can think of this setup as being pretty straightforward, pretty typical every single time, is moles of water on top divided by moles of water on bottom plus whatever extra ions you get from the solvent, or sorry, from the solute. So 8.32 divided by our sum on the bottom. And we get a mole fraction of water that's about 0.847. And so we're going to take we're going to need the vapor pressure of above the solution is going to be this mole fraction of water, which is 0.847, times the pure pressure that they give us in the question, which is 17.4 torr. So I'm not going to do any really conversion to atmospheres. I'm just going to leave it in torr. And so I'll leave my mole fraction in the calculator and then multiply by 17.4. And it's essentially a percent calculation, which is what a mole fraction essentially is. But the adjusted vapor pressure of water with the extra ions in solution is about 14.7 torr. And that's your answer. So the biggest trick is just figuring out the mole fraction, making sure that this multiplier for the ions when it's dissolving is that step is happening. So use the total ions in the solvent calculation, and then that mole fraction of water of the solvent is being multiplied by the pure vapor pressure, which was the 17.4, and you get the adjusted vapor pressure of your water now that ions are dissolved in it. Let's go and clear this up, and we're going to look at what the next section is going to give us. So now if you have multiple liquids and both of them are volatile, I mean they both have their own vapor pressures, it's the very similar setup where you're taking a mole fraction multiplying by the pure vapor pressure of that substance plus the mole fraction times the vapor pressure of the second substance. And you can add those together, because essentially what you're doing is find the total pressure by adding the vapor pressure of one liquid plus the vapor pressure of another liquid. It's just for each of those vapor pressures, they're being affected by their own mole fractions. And so you have to find their mole fractions. And what you're calculating is this vapor pressure of solution, which is that green line on the graph there. That's the ideal vapor pressure. Now, this is the one that generally gets augmented a little bit because the liquids are interacting with each other. And if they're interacting strongly, then the vapor pressure should go down. If they have a weak attraction to each other, then the overall vapor pressure should increase because they want to escape. They're not held into solution as long. So you can see this caption here, ideal solutions have this nice connection between vapor pressure. And I'll kind of construct this graph from scratch for us. And this, we have the positive deviation, means the vapor pressure that we observe is actually higher than expected, or this negative deviation where the vapor pressure that we observe and measure is actually lower than our calculations, which is our expected value. Anytime we have an expected value, that's a calculated value. You actually have to go into a lab and observe it, and that's just some raw data that you would collect in a lab, and that's, you can compare the two. There's a whole explanation of positive and negative deviations. There's not a whole much to write here, but let's go ahead and do an example together. So I'm going to explain the vapor pressure of two liquids, same solution concept, and I'm going to explain the graph. I'm going to construct it from scratch. This is something I can definitely do again in class, and actually none of your homework questions are based on this last little part, but let's take a look at some sort of solution. Here we go. And so here's a solution. Let's say this is some sort of water and alcohol, like water and ethanol. And they both have their own vapor pressures. So let's say water's vapor pressure, we're going to say that's our first substance, pressure A, and we're going to have some vapor pressure of water. And then here's our ethanol, and whatever its pure vapor pressure is, it's just B. Here we go. And so if I look at a solution that compare it to just a solution that would be 100% water, if it's 100% water, then the mark I would make on this y-axis would be just the pure vapor pressure of water. And on the other side, if I look at a pure solution of just ethanol, I say it's 100% ethanol, and I put a mark on the graph and say this one is 100% ethanol. Okay, I wanted to double check what the actual pure pressure of ethanol is. It's actually up here in the 40s. And so the ethanol evaporates much faster than water does. Ethanol does have hydrogen bonding, but water is smaller and has more efficient hydrogen bonding. So water is more likely to stay in solution, whereas ethanol evaporates a little faster. So as we mix these, whatever percentage we mix them, the vapor pressure of the solution is going to be somewhere in between. So the space in between is based off the mole fraction. As we add, let's say if we start on the far left side, we have 100% water. As we add ethanol, the mole fraction ends up being somewhere in between. And so they meet each other in the middle at some sort of 50%. Let's say we have a 50-50 solution, half water, half ethanol. We would expect that the vapor pressure would be somewhere right in between. If I draw a straight line between these points, let's say the pure vapor pressure of water is about 17. I'm thinking like room temperature, somewhere between 17 and 18 torr. And ethanol is up in the 40s. I think it's like 44-ish torr at room temperature. And so if I were to make a 50-50 mixture, under ideal circumstances, the vapor pressure would be right in between, because that would be a mole fraction of 0.5 for water and 0.5 for ethanol. So I'd have their pure pressures, add them together, and I get some sort of total vapor pressure. So the total pressure of the solution is based off of the mole fraction of water times its pure pressure, and that gives you the vapor pressure of just water, and then the mole fraction of ethanol times the pure pressure of ethanol, and that gives you the vapor pressure of just ethanol. They don't really, you kind of do those calculations separately and you just add them together. And it turns out it's right in between when it's a 50-50 solution. Now this is ideal. This is ideal. This is expected. This is our calculated value. The problem is when we go in the lab and we actually measure this, it's not going to be 100% ideal, because water and ethanol can hydrogen bond with each other. They actually have pretty strong intermolecular forces, so they're going to hold on to each other more than expected. So let's say the trend changes actually below. I'm kind of being a little bit dramatic with how I'm drooping this, but not drawn to scale. Let's say this 50-50 pursuit is actually observed down here. And so the pressure observed is lower. So we're going to go, hey, what is this ideal pressure? What is this calculated pressure compared to the observed pressure? If the observed pressure is less than the calculated pressure, here's the calculated value. If what we observe is less than, we call this negative deviation. The observed vapor pressure is less, so negative. This is due to strong attractive forces between the two substances, like hydrogen bonding. But let's say we throw some volatile liquid in there that doesn't really jive with water very well, not as admissible, doesn't have the vapor pressure is kind of weak. And anytime you have a vapor pressure that's higher than expected, evaporates more than expected, the particles might even repel each other a little bit and just kind of have a positive deviation above where the observed is higher than expected, our calculated values. But for this example, it would be best to assume that this would observe negative deviation because both of these can hydrogen bond with each other. Nope, you can see I made a whiteboard out of our background. There we go. So I wanted to go to this is something to explain a little bit more in class. And I wanted to go to a couple of homework questions and I'll let you go. And you can do your best and come back and we'll talk about it in class. And voila, here's our assignment 10. And we're down to the last part. So adding a solute to a solvent extends the liquid phase over a larger temperature range. Yes, anytime you have a solute inside water or some sort of solvent, you're extending both the liquid range in both directions. And I explained that in class to both of the classes. So whenever you look at types of solutes like sugar or urea, I'm thinking, does it dissociate? By how much? These are both examples of non-volatile solutes, so they don't evaporate, and non-dissociative solutes, meaning they don't separate into ions. They're also categorized as non-electrolytes if the ratio of dissolving is 1:1. Every time we throw in one of these sugar molecules, it has a ×1 effect on the number of ions released in solution because there aren't any extra ions in solution. And the urea would be the same thing. Any sort of covalent compound, like carbon dioxide, you're not going to ionize and break it up into smaller pieces when they dissolve. And that's how they're different. They don't conduct electricity. That's in the category of non-electrolytes. Whereas calcium chloride is an electrolyte. It's a strong electrolyte because it separates and has that ×3 effect. So for equivalent mass of all three of these, calcium chloride has a much bigger effect on any sort of boiling points or melting point because you have more ions in solution. More ions, greater effect on vapor pressure, melting point, and boiling point. And anytime you add stuff to water, you have the 100 degrees Celsius, there's your boiling point. And then you have the 0 degrees Celsius, there's your freezing point. You're extending the liquid phase. So the boiling point would increase to some higher values, so it takes longer to boil. And the freezing point decreases to some lower value in the negative Celsius. And so ice changes to water at a lower temperature. Here's your solid. There's your liquid range lowering. So let's say this goes down to -5 degrees Celsius. That ice is going to melt at -5 then instead of 0 degrees Celsius. So in colder temperatures, there's less likely to be ice on the roads. So let's get a couple of the calculations. So we have, let's see, 59. We have some mass of glycerin, which is assuming that glycerin is non-volatile, so it doesn't have its own vapor pressure, and it's a non-electrolyte solution. That means it's going to dissolve with a 1:1 ratio, so you're not going to have to double the ions or anything like that. How is this going to affect the pure vapor pressure, 113 torr, of ethanol, which we have a mass value as well? So whenever you have a mass value, change those into moles. Moles of glycerin, so you have to calculate the molar mass using the periodic table. Change ethanol's mass to moles, and define the pure, or define the vapor pressure of the solution, which is going to be our answer. We're going to take the mole fraction of ethanol, moles of ethanol on top, divided by total moles on bottom, times this vapor pressure, this 113. That's the pure pressure of ethanol if it was just by itself. And then that's it. You got your total vapor pressure. Again, this is a times one effect. Once you separate the glycerin once you get moles of glycerin, you don't have to double that because glycerin is a non-dissociative solute. A good question about 32 or 62 is just looking at the equation and manipulating for what you're trying to solve for. So we have benzene, which has a vapor pressure. So let's let that be our solvent. Here's its pure vapor pressure. And so when I look at the equation, the pressure of the solution is the mole fraction of benzene times the pure pressure of benzene, B for benzene. So this 0.93 goes in on the far right side. I'm going to put 0.93 in there. And we have a non-dissociating, which means that's a times one effect. Non-volatile, so we only have to consider the vapor pressure of benzene. Solute, and here's a mass of, 10 grams of a non-dissociating, non-volatile solute. We don't know what the solute is, and we're actually going to figure out the molar mass of the solute, but we do know how many grams are involved. And we know the total pressure, so I'm going to go ahead and plug that in here, 0.9. So the molar mass is my final question, which is grams per mole. I have the 10 grams. And all I need to do is figure out how many moles are in solution and divide, and I should get the molar mass. And we can get that moles from our mole fraction. If we rearrange this and solve for the mole fraction, that's 0.9 divided by 0.93. So the mole fraction is 0.968 rounded. But that doesn't tell us moles, that just tells us the mole fraction of benzene, but we do know 78.11 grams of that is benzene, C6H6. And so if I do a calculation of 78.11 divided by the molar mass of benzene, which is 6 carbons and 6 hydrogens. So 6 times 12 is 72, plus 6 hydrogens is another 6. And each of those have a 0.1 on there, so that's going to be 12 of those. So it's 78.12 should be the molar mass of benzene. And when I divide those, you see that it's pretty much the same. 78.11 is essentially the molar mass of benzene. So this is meant to be about 1 mole of benzene. So the numbers work out pretty nicely. It's like 0.99987, something like this. So it's just around to 1 mole of benzene. So if we have the mole fraction being 1 mole of benzene, and on the bottom it's the total moles. So we have 1 mole of benzene plus some number of moles. I'd use X, but mole fraction is already X. Let's just say moles of solute. Let's just fill S for moles of solute. If we figure out what this is, no, I don't even like that. I'm just making it a different color. Here we go. There's an X. If we figure out what that is, set it equal to 0.968, solve for our unknown value. There's our moles, and we can plug it in here and figure out the molar mass. And there's your answer. Pause it so you can write this down. All right, last part. This is the most common kind of questions, this last part. So 67 and 68. I'll do this one Really quick on the backside, you're just trying to figure out positive deviation, negative deviation. So ones that have positive deviation are ones that do not have a strong intermolecular force. So like polar and nonpolar. So I would just say that the ones that do not jive with each other the most is D. We got nonpolar and polar. These are not really interacting with each other as well. This is most likely to be the first graph. This is most likely to be positive deviation. Whereas anytime they have the same type of intermolecular forces, both LDFs, even though this is they're both kind of the same structure, this is the one that's going to be the most ideal. There's not a whole lot of difference between these. And then we have dipole versus hydrogen bonding, and then hydrogen bonding and hydrogen bonding. So these ones are pretty same, whereas these ones are a little bit different. So we're going to be looking at the most ideal, generally have relatively weak attractions, which is going to be our choice C, I would say is the most ideal. Any sort of negative deviation are going to be some sort of hydrogen bonding, like choice B. I would say A could probably also be the ideal solution, graph C, because A, yeah, they're both polar, but they're not hydrogen bonding with each other. So they're both polar and polar, but there's no additional extra really strong force. But we can always check the back of the book to see what the book intends for that one. So 67 to 68. So we are trying to just figure out which of these solutions or how each of these solutions would affect some sort of vapor pressure, which would have the lowest vapor pressure. So low vapor pressure means high number of ions. The more ions, high ions, or high parts of solute means the low vapor pressure is going to go down. So these are opposite each other. So we have pure water. Okay, so we have some standard here to set. So anything we add to water should bring that vapor pressure down. So I was going to say pure water probably doesn't have the lowest vapor pressure. Choice D is methanol in water, and the vapor pressure both methanol and water is 143. And so that vapor pressure is even higher. So in terms of which is the highest vapor pressure, it's probably choice D. Throw methanol in water. The vapor pressure is going to go up compared to pure water. So let's just differentiate between choices B and C, because those are ones that are solutes going in water. Glucose is a covalent compound with a ×1 effect. So if the mole fraction is 0.01, so same moles of both, but sodium chloride has a ×2 effect, that's going to be the most ions in solution. Most ions in solution is going to have the lowest vapor pressure. So choice C is correct for 67 or 68. The highest vapor pressure, throw that methanol in water, that vapor pressure goes up compared to pure water. There's more examples we'll do on Monday when we get back. Finish this, and we will be in a good spot to go over it when we get back. We only get a couple days when we get back before we're going to quiz on this, and we got to move on. Have a wonderful Thanksgiving. I am thankful for all of you sticking through this video and persevering through this semester. It is not easy, and I really appreciate it, and I really enjoy working with all of you. So take care, and I will see you in a week.